Good morning, everyone. Today, we are diving into the fascinating world of motion trajectory planning. This is a core technology that sits at the heart of robotics, autonomous driving, and advanced manufacturing. At its simplest, the goal is to figure out how to get an object, like a robot arm or a vehicle, from a start point to a target. But it's not just about the path. We need to define the entire journey over time. We have to specify exactly where the object should be at every single moment, and also determine its velocity and acceleration along the way. It's the difference between knowing you need to drive to a neighboring city and having a detailed schedule that tells you when to accelerate on the highway and when to slow down for a turn. This process ensures that motion is not only possible but also smooth, safe, and efficient. To build a solid foundation, we first need to differentiate between two terms that are often confused: path and trajectory. Think of a path as the geometric route. It answers the question, which way do we go? For example, to get from point A to point B, you might need to pass through intermediate points P1, P2, and P3. The path is just a set of points in space. A trajectory, however, builds upon this path by adding the critical dimension of time. It answers the question, when do we get there? It gives us a function of time that specifies not only the position at any given instant, but also the velocity, acceleration, and even the jerk. So, a trajectory is a path with a strict timeline. It tells us, for instance, to accelerate for 2 seconds, then coast, and finally decelerate to a precise stop at the 10-second mark. Every trajectory must respect real-world constraints. Kinematic limits, like maximum speed, and dynamic limits, such as motor torque, define what a machine can physically do. We must also avoid obstacles and meet task-specific requirements. Based on these boundaries, we choose an optimization objective, whether to minimize time, energy, or jerk. With goals set, we begin global path planning. This is like using a GPS to find a rough route on a map, avoiding all static obstacles. For this, we use algorithms such as A, which is fast and efficient. In more complex, high-dimensional spaces, like those for robot arms, we apply sampling-based methods such as the rapidly exploring random tree RRT, which quickly finds a feasible solution. This first step gives us a rough path to refine later. The path generated in the first step, by an algorithm like A, is typically a series of straight-line segments forming a jagged polyline. If you tried to command a robot to follow this path directly, it would have to come to a dead stop at every corner, which is inefficient and causes immense stress on the machinery. So, our second step is path smoothing. The goal here is to turn that discontinuous polyline into a smooth, continuous curve. We do this by fitting curves to the path. Common techniques include spline curve interpolation, where we use mathematical functions like B-splines or Bezier curves. These are great because they can ensure continuity not just in position, but also in higher-order derivatives like velocity and acceleration. This results in a path that is physically feasible and much smoother for a machine to follow. We now have a smooth geometric path, but it's still just a line in space. Our third and final step is trajectory generation, where we bring in the time dimension. We need to decide how fast to move along that smooth path. This is done by defining a motion law or a velocity profile. The simplest method is the trapezoidal velocity profile, which consists of constant acceleration, constant velocity, and constant deceleration. It's easy to implement but results in jerky starts and stops. For smoother motion, we use an S-curve velocity profile, which rounds off the acceleration and deceleration phases. This ensures continuous acceleration, leading to much smoother motion and reduced vibration. For advanced applications, we use time-optimal planning, which considers the path's curvature and system limits to minimize the total travel time without violating any constraints. These planning concepts are applied across a huge range of fields. In industrial robotics, we see point-to-point motions, like pick-and-place tasks, which often use S-curve planning in joint space. We also have continuous path motions, such as welding or gluing, which require the robot to precisely track a complex path in Cartesian space. For mobile robots and autonomous vehicles, planning is split into two layers. A global planner finds a route on a map, while a local planner, like the dynamic window approach, reacts in real time to dynamic obstacles using sensor data. Finally, for drones or UAVs, the challenge is to generate smooth 3D trajectories that respect aerodynamic limits, often using optimization techniques like minimum snap to create incredibly fluid flight paths. Let's wrap up with the key takeaways. First, motion planning is inherently hierarchical, moving from a global path to a local trajectory that is sent to the low-level motion controller. Second, smoothness is critical. Ensuring continuous acceleration, for example by using S-curve profiles, is vital for reducing mechanical shock and improving tracking accuracy. Third, we must always respect the system's constraints. A plan that violates physical limits is useless. And finally, there is no single best method. The right algorithm depends entirely on your specific application, whether your priority is precision, real-time speed, or operating in a dynamic environment. Thank you for your listening. This is the end of session 18.